Welcome to the session on protection and coordination analysis. In this session, we'll understand the criteria for protecting the equipment and coordination or selectivity criteria in order to perform protection and coordination analysis. So here we'll cover various objectives for the protection. So the objectives define what all it should cover while you protect the equipment and the entire electrical system. So the first objective is human safety. So when you apply the protection, it should consider the human safety which prevents injury and fatality. The next objective of protection is equipment protection. So when you apply any protection to the equipment, it should allow the normal operation and isolate the equipment in case of abnormal conditions. So the objective is to protect the equipment from the damage due to various abnormal conditions. The next objective is protection of system, which considers the stability of entire system. So the protection of entire system should be designed in such a way that entire system stability can be maintained when you apply the protections such as under voltage and over voltage protection, under frequency over frequency protection, rate of change of frequency, and islanding of the system. So when you apply the selectivity to the protection system, the minimal isolation of the network is expected during abnormal conditions, and it should permit the normal operation for rest of the electrical network. So here you can observe that if the system is not selective, which is without selective coordination, if the fault is applied at this point, the protection device is shown in red will open, which causes blackout of entire system. Now with selective coordination, if fault is applied here, only the protection device close to the fault will sense this fault and isolate the faulty component from the system without affecting the remaining electrical system. The next objective is reasonable cost, where it should achieve the maximum reliability for protection and coordination with minimum cost. As we are aware that applying protection to the electrical system is a science, experience, and art. So when you apply the protection system, it should be sensitive to the faults and insensitive to the normal operation. It should clear the fault as fast as possible with proper selectivity margins, minimal isolation of faulty area, and it should have the capability to operate correctly under all predictable power system conditions. So we'll discuss various international references which are being used for protection and coordination of electrical system. One can refer IEEE 242 standard, which is IEEE recommended practice for protection and coordination of industrial and commercial power system, which is called IEEE Buff Book. Another reference is IEEE 141 standard, which is IEEE recommended practice for electrical power distribution for industrial plants, which is also called IEEE Red Book. Few more references are IEEE 399, which is IEEE recommended practice for industrial and commercial power system analysis, and it is called IEEE Brown Book. You can also use any other technical references which are accepted and being used globally. So let's understand the study procedure for protection and coordination analysis. So the first step is to prepare an accurate single line diagram with its CT and relay information. So once you have created a model for load flow and short circuit analysis, you can add the CTs and relays to that model. Next is to obtain the available system current spectrum. Here we need to find out the current spectrum starting from the operating load, overloads, and fault current. Next is to determine the equipment protection criteria. Depending on the type of equipment to be protected, you need to decide the protection criteria for that equipment. Select the appropriate protective device and settings. So here you can select various make and model of the protection devices. Next is to plot the fixed points. So the fixed points are defined as various operating characteristics such as motor starting characteristics, damage curves for various electrical equipments, full load ampere, cable ampacities, and so on. Now, once you have plotted these fixed points on the time current characteristic curves, you can plot the relay characteristic curves and analyze the results. Here we'll discuss the required input data for protection and coordination study. So in order to model the electrical network, we require one line diagram including its all relay and protection details. If your system is connected to an infinite power grid, it requires three-phase and line-to-ground fault current and protective device settings for interface. Now, apart from this data, we require input data for various electrical equipment such as generator, transformer, motor, load, system fault currents, cable and conductor, bus or switchgear, instrument transformer, and protection device data. So in electrical system, there are various electrical equipments for which protection needs to be designed and implemented. So the major equipments are induction motor, synchronous motor, cables, transformers, generators, bus bars, transmission and distribution lines. So let's understand equipment protection criteria. So while you're applying the protection to various electrical equipments, it should allow the normal operation of that equipment, where it should consider various other conditions as well, such as maximum permitted current, operating temperature, cooling media, elevation, etc. It should protect the equipment against the abnormal fault conditions. Now, these abnormal conditions can occur because of excessive through fault currents, improper design, installation, or operation of equipment, and through various incidents. As you are aware that all the electrical equipments have their maximum operating limits, it is also called the damage curve. So such damage curves has to be plotted for various electrical equipments in the time current characteristics. Here we will understand the operating and non-operating region for protection relay. So this view shows the time current characteristic in ETAP software, where the characteristics of relay equipments etc. are plotted. So this line shows the operating characteristics of equipment, which is in this case the starting curve of induction motor. These two lines shows the damage curve of equipment, which is hot start and cold start rotor damage curve. So while applying the protection to the equipment, it should be set above the operating characteristic and below the damage point of the equipment. So the actual relay characteristic should be set somewhere in between these two curves. So here IDMT relay characteristics is shown above the operating characteristic of equipment and below the damage curve of equipment. Now once you plot the relay characteristics, the region below this relay characteristic is called the non-operating region, and the region above this relay characteristic is called the operating region. Now here let's understand different protection types. So first we'll understand overcurrent protection, where it includes inverse time overcurrent, instantaneous overcurrent, directional and differential. Next is impedance based protection, which is also called distance protection. So distance protection can be applied to the transmission lines. Next is voltage protections. So the voltage protection covers under voltage protection and over voltage protection, which can be applied to the entire electrical system. Next is frequency protection. It can be further defined as under frequency and over frequency protection. Now let's understand overcurrent protection first. The electrical system has protection elements at various levels, and these protection elements are low voltage circuit breaker with trip units, MCB, MCCB, ICCB, fuses, overload relays, IDMT relays, etc. So when you apply the overcurrent protection to the system, you need to select the relay characteristics, define the pickup, and decide the time margin at higher fault current. When you are coordinating the downstream and upstream curve, you have to define the time margin at maximum fault current. So in order to apply the overcurrent protection, you need to consider the proper relay characteristics such as standard inverse, very inverse, extremely inverse, or long time standard earth fault. And the equations of these characteristics are defined in IEC 60255 standard. So if we consider the equation for standard inverse, which is operating time T is equal to TMS into 0.14 divided by IR raised to 0.02 minus 1. So here IR is equal to fault current divided by pickup current. TMS is time multiplier setting and small t is relay operating time in second. So you have to understand that all the characteristics are plotted at different values of TMS. So let's consider an example where we have used standard inverse characteristics which uses this equation. So here we have considered the CT ratio as 200 by 1 and the curve type is selected as ICA or IC standard inverse. So here we have set the pickup of the relay as 100%, which is 1 ampere in terms of CT secondary or relay side. So here we have calculated various operating time of the relay at TMS is equal to zero point 0.5 for various fault currents. Now if we compare the operating time of this relay at 3 times, 5 times and 8 times of the pickup value, which is 200 here, which is 3.15, 2.13 and 1.64 respectively. Now we can plot the same curve using the same parameters in ETAP and cross check the value of operating time for this relay. So now I will switch to ETAP in order to understand the various operating times for various multipliers. So here I have plotted the relay characteristic on TCC in ETAP. So we have considered the pickup as 100%, which is 1 per unit, and the time dial of 0.5. So as we have seen at 3 times, 5 times and 8 times of pickup current, the operating time for this relay is 3.15 second, 2.14 second and 1.65 second, which is matching with that Excel sheet. Now as you can see, this is the fault current arrow which shows 2 kiloampere of fault current. So when there is a fault of value 2 kiloampere, this relay will operate at 1.48 second. If the fault current value is 2 kiloampere or 2000 ampere, the operation time of the relay is 1.48 second, which is matching with the ETAP software. Now you can observe one thing here. The operating time of the relay is same. It means the relay characteristic becomes definite after this point, which you can observe in ETAP as well. So after 4000 ampere, the relay characteristic becomes definite. So now we'll understand various low voltage protection devices. So the first one is MCCB trip units. So MCCB will have thermal magnetic trip units. As you can see in this curve, this part is thermal, which is fixed, and this part is called magnetic, which can be either fixed or adjustable. So if you look at the MCCB trip unit, you will find such similar settings available in the front side of this protection device. Now next is MCCB trip unit with magnetic characteristics only. In magnetic characteristics, you will have instantaneous protection where you can adjust this device for various current spectrum. However, the operating time of this trip unit will be fixed. So next is low voltage circuit breaker with trip units. So the low voltage circuit breakers are available with solid state trip units or microprocessor based trip units. So there are various segments in trip units which can be defined as long time, short time, and instantaneous. So this is the characteristic for solid state trip device, where this part is long time pickup, long time delay, short time pickup, short time delay, and instantaneous characteristic. So here we'll understand the protection by power fuses. So as you are aware that fuse is a non-adjustable device which has continuous and interrupting rating, and the characteristics of the fuse is identified by minimum melting and total flaring time. So this is the fuse characteristic where the lower band is minimum melting curve and the upper band is total flaring curve. There are various type of fuses available in the market. Some of them are expulsion type, current limiting fuses, and electronic fuses. So let's understand the application of current limiting fuse. So it limits the peak current of the short circuit, reduces the magnetic stresses and thermal energy. So in this figure you can observe the electrical system operating under normal operating condition. Now at this point if fault occurs, the system will see the peak value of fault current. So at this fault location, if fuse is available, it will limit the fault current to this value and clears the fault in less than half cycle. Current limiting fuse is a better short circuit protection. Non-CLF or expulsion fuse is a better overload protection. And electronic fuses are typically easier to coordinate due to the electronic control adjustments. Now here we will understand how to apply the motor protection. As we have discussed earlier, we need to find out the fixed points such as motor starting curve of an induction motor, as well as the damage points such as cold start and hot start stall time of an induction motor. Once you get these points, you can plot the relay characteristics which will protect the motor against the fault. So these are the various international references for motor protection. Some of them are IEEE 620, IEEE 1255, NC or IEEE C37.96, NEMA MG1 motors and generators, and The Art of Protective and Relaying book by General Electric. Now here we'll understand the cable protection. On TCC, you will find a green line which is a cable damage curve, and the relay characteristic has to be set below the cable damage curve. These are the standards which are being used for cable protection. Transformer protection is similar to what we have understood about motor and cable protection. So the relay curve has to be set below the transformer damage curve, which you can observe here. So the transformer damage curve is shown with TR1 in orange lines, and the relay curve which is shown in blue is set below the transformer damage curve. These are the standards which can be referred for transformer protection. Now so far we have discussed the protection criteria for equipment protection. Now here onwards we will discuss the rules for selective coordination. So for selective coordination, the downstream device curve should be located to the left and below the upstream device curve for various current spectrum. The second rule is sufficient time margin for operation of the downstream protection device should be provided before upstream operates. So in this electrical network, there are two relays which are named as RD, which is downstream relay, and RU, which is upstream relay. So if you coordinate these two relays for a fault FD, the curve of relay RD should be below the curve of relay RU at the fault current of FD. Now, as we have defined in the second rule, to maintain the sufficient time margin. So how we can decide the sufficient time margin between these two relay operations? So there is a guideline given in IEEE 242 standard which says the total coordination time should be maintained as zero point 0.3 second or 300 millisecond for electromechanical delay and zero point 0.2 second or 200 millisecond for static or numerical delay. So these values are derived considering the circuit breaker opening time, relay over travel time, and various relay tolerances and setting errors. So if you add all the components, you will get the total coordination time. Now this coordination time may vary depending on the circuit breaker opening time in actual and the type of relay. Now this coordination time interval is applicable when you are coordinating two different relays. However, there is a guideline given in IEEE 242 standard if you are coordinating two different protection devices. So here it shows various downstream connected devices and this will show you upstream connected protection devices. So if you observe, if you are coordinating fuse to fuse or fuse to LVCB or LVCB to LVCB, CS is written. So CS is explained here as the clear space between the curves. So if you are coordinating fuse and LVCBs, you don't need to provide any coordination time interval or time margin between these two protection devices. So you can keep very less clear space between these two protection devices without applying any intentional delays. You have to make sure that upstream and downstream device should not overlap with each other. So if you are coordinating two electromechanical relays, the time margin should be 300 millisecond. And if you are coordinating two numerical relays, the time margin should be 200 millisecond. So for a balanced system, all the phase current will be same. So the residual current IR or 3I0 which will be passing through the relay will be 0. For any unbalanced fault, the phase fault currents will not be equal and the residual current will pass through the relay and relay will operate. So this slide shows you the relay NC number which is used globally for various make and manufacturers of the relay. So here the term P is used for phase, N for neutral, G for ground, SG for sensitive ground. This will end our session here. Hope you have found this session useful and informative. Thank you.